Hello and welcome to another episode of the Oxford Online Maths Club. My name's James and today it's just me on the live stream and I'm going to try and tell you about fluid dynamics. That's the plan for today. First, quick tech check. Several things have changed for this week. Firstly, daylight savings time happened in the UK. Sometimes I remember that's coming and I tell people about it for the club so that people watching outside the UK get a warning. This time I forgot. So it's a real pleasure to see that some people have changed their clocks and are here today. Hi Ali, hi anonymous person, hi Alfie and Harriet in chat. People are joining us in chat live at slido.com/OOMC if you want to join in. Hi to Zach, hi to another anonymous person, here they come now. Brilliant, great, and no one's telling me they can't hear me, no one's telling me they can't see me, so I think we're live, so anything could happen. Also joining us, moderating chat today, very helpfully, thank you, is Imi. You met Imi a few weeks ago for metrics. Imi is now helpfully approving chat messages and things so that they can appear even when I'm not pressing any buttons. Amelia's here. Yes, hi, Amelia, yeah. Brilliant, right, cool, okay. Amelia maybe met this person. Right, okay. It's really nice now that we're doing some in-person events again that people can actually come in person to Oxford sometimes as well. We're still taking bookings at time of recording for the open day on the 30th of April. So if you're free and you can make it to Oxford on the 30th of April, there's still some places left on that open day. Great, okay. I think I'm going to get going with some maths if that's all right. Yeah, Harriet, so all adds up too. Good, okay. So what I'm going to do is I'm going to put fluid dynamics at the top. So we've got a title. And I'd like to describe the problem that I'm going to try and do. I'm also going to write it down so that as people join a little bit late, they can say hi and also see what we're doing. I would like to try and explain the shape of a tap. I guess I don't mean the actual tap, I mean the water coming out of a tap. So I'm going to put tap, what shape, question mark. What a great summary of what I'm going to do. I think what I'm trying to describe is the way that water, when it comes out of your tap, has a shape like this, sort of gets narrower as the water falls. Let's try and draw that, there we go. Something like this. Not shown, actual physical tap, just the water, because that's the bit I'm really excited about for fluid dynamics. Tell you how, there's going to be an enormous amount of maths at the open day. We like putting a lot of maths into our open days, so that as well as telling you facts about the course, we can tell you some maths as well. We've got math speakers by different math speakers talking about different maths topics. That's a big chunk of the day. Good. Okay. I'd like to know what shape this makes. So we're going to do some modelling assumptions, I suppose. We're going to have some approximations maybe. But I'm going to try and describe what shape this is as the water comes out of the tap and falls. Okay, so I'm going to write falling water next to it as well. Okay, under gravity, I suppose. It's actually a classical problem that people did quite a while ago, so we're in good company here, historically, thinking about people who've done this calculation before. But it's an interesting exercise, I suppose, because what I really want is, I suppose, the shape as a function of, I'm going to use z as my variable, I think. So I'm going to put my little coordinate system in. Maybe I've got an x variable and a y variable and then z. Sometimes when they're describing things like this, people use z pointing downwards, but that makes me feel a little bit uncomfortable. So I'm going to use z pointing upwards and say how things are falling down. So maybe this is z equals 0 over here at the top where it comes out of the tap, and then this is z negative over here where it's falling. Okay, then it fall down. For the Maths Open Day, will we get to see a bit of the rest of the university? There is an opportunity for college tours. When you book for the Open Day in April, there's an option to book for one college tour. and the rest of Oxford is a town that you're welcome to explore. There's other open days later in June, especially relevant if you're watching the replay of this video at some point later. There's other open days in late June where every department and every college are open, big university open days, loads of people all around Oxford, loads of different things are open. Those ones have more of everything and less maths in particular. People are trying to do so many things. SV, I've been trying to sell the open day on the 30th of April. Thank you for another chance to mention the open day on the 30th of April. Sign up on the maths department website, which has just been redesigned. So if you join us via the maths website, you might have noticed that the maths website has been a little bit revamped today. So at time of recording, all the pages look a little bit different, and there's some broken links. If you find a broken link, don't let me know this week. We're still fixing them. Okay. It's like one of those shapes, says Rory, like a thickening cylinder. Like a cone but with no apex. Oh yeah, okay. I know what that shape's called, so I'm going to remind Rory what that shape's called. Rory's describing this shape, which is like a cone with the top chopped off. I've drawn a very short one, but you can also measure a tall one. I think those are called frustrum. I think I've got the right number of R's. Frustrum? A frustrum of a cone sometimes? Yeah, maybe it's a bit like that. It gets narrower. The way I've drawn it, and also the way I think it works, is that it gets narrower, but the rate it's getting narrower, I think I expect that to slow down. Because if I extend Rory's frustrum, if I keep going, if the water keeps falling, then we're going to get down to a cone at some point. And I think I'm expecting this to sort of keep going and to not hit a cone. So it's something a bit like a frustrum maybe, but the other way up and maybe not quite so pointy in the end. What a strange thing to say. Strange thing for me to say. Right, cool. Okay. Is the classical problem Gabriel's horn? No. I think this is the classical problem that we're about to do. And no Gabriel yet. Ooh. T-level. Are you sure Oxford Open Day has maths in it? It's my open day, I'm in charge of it. Yeah, there's loads of maths. I've got Vicky Neal on the schedule talking about elliptic curves amongst other things. So if that's not maths, then I don't really know what is. Is it not frustrum? Frustum. Oh, James learning to spell live. Let's go, chat. Frustum. It is frustum. I had the wrong number of R's. Thank you, chat. Learning to spell. Welcome to the Oxford Online Maths Club, where today we're learning Latin spelling. I should not say it's Latin. That's the next thing chat will correct me on. Thank you, chat. Nameless in chat, and thank you, anonymous. Here we go. Yeah. Okay. So what Alfie says, maybe we're revolving a function around the z-axis. This is something you learn in further maths. I think these shapes where you revolve them around the axis. I think you do a whole bunch of maths about the volume and surface areas of those. Oh yeah, I've done a trailer now. Maybe this will continue to be an advert for the open day. Elliptic curves, maybe. Just a little bit. But just enough to convince you that what you really should be thinking about doing is coming to university and learning about elliptic curves. This is like a trailer for a trailer, because the open day itself works like a trailer. Anyway, never mind. Right, okay, let's put some variables in. I'm going to draw a bigger picture as well, because this was a good diagram, but I want a really big picture. My teachers in school were always telling me to draw bigger pictures. There you go. Something like this. I paid to broadcast all of these pixels. I'm going to use all of the pixels. Right, okay, so maybe this is the top. Z equals 0. And I might imagine that up here, there's some velocity. Well, I suppose velocity all the way through. But I might imagine there's some velocity at the top, and some velocity at the bottom. So maybe I'll set up some velocity. I'll say maybe I've got some fluid velocity, v of z. So v depending on z. Velocity v seems like a sensible letter to use for velocity, and I'm going to say it depends on z. I'm thinking about how maybe the water's speeding up due to falling under gravity. Maybe that's not the obvious thing to say first. Maybe the obvious thing to say first is that I'm going to think about circular cross sections. all the way down. I'm going to think about circular cross sections all the way down, and maybe I'll say that they've got radius r of z. So maybe this radius, which is maybe the thing I really care about if I want to know the shape of this falling water. Maybe I really want to know the radius of that cross section, or even the cross-sectional area. So I'm trying to put in lots of words as well so that I can talk using words. No maths yet, just describing the problem that I want to do. I guess cross-sectional area, I think I want to call capital A of Z. Okay. So these things are going to depend on Z. The further down you go, the stream of water, these variables are different. Different velocity, different radius, different area in different places. Okay. Oh, I think I can do a tiny bit of maths. Yeah, oh my word. People are good at some people know about rotating shapes around axes, and we've got a bit distracted, I think. Oh, right, okay, logarithms are in chat as well. I haven't got any logarithms yet, but I do have the area of a circle for you. This is one of those moments where chat's operating on a different level from me. I've just noticed my cross-sectional area, I suppose, is pi r squared, which I'm going to be really explicit and write r of z squared. So I've got my area, it's pi times r z squared. So I think my constraint is that the variables can depend on z. I'm assuming that the stream of water has a circular cross section all the way down. Partly because that feels a bit realistic, mostly because it makes the calculation a lot simpler if I make assumptions like that. Feels about right, you know, rotational symmetry. If my tap's round, then you kind of expect the water to be round when it comes out. Fair enough, I suppose. Okay. I'm also going to say at the top where z equals 0, I'll say we'll start. This is maybe the size of my tap or something. I'll say radius up here, r of 0. I'll give that a name. I'll call that r subscript 0. And the velocity that it initially comes out of the tap with, something complicated to do with plumbing. Let's not think about it too much, but I'm going to call it v0 for the velocity. SV's here. I think I'm just thinking about how water falls. At the moment, it could be any shape, but we're going to use some facts about how things fall in just a moment. Because maybe now that I've set this up with a v0 as an initial velocity, and we've got some idea about falling, this feels to me a bit like those problems you do in A-level mechanics, where you've got some initial velocity and the thing's falling. So there's some sort of Suvat equations that I'm aware of. Let's be a bit careful. What I want to think about is what's happening to a little bit of water. So if I take some of the water molecules that are coming out of the tap, speed v0 due to all of the plumbing and stuff in my house, speed v0 coming out of the tap, then when they get down here, I've said they're going at speed v, and there's some sort of Suvat stuff you can do to work out how to do with acceleration and gravity. I'm going to think about it in terms of energy, I think. So I'm going to write energy over here. And in fact, we're going to go over here in just a second. Okay. So, in terms of energy, when this little bit of water comes out of the tap, it's got kinetic energy because it's moving at speed v0. So its initial kinetic energy is half mv0 squared. And I've said that the top is z equals 0, so I'm going to say it has no gravitational potential energy when it comes out of the tap. That's just convenient, I suppose. It's a good trick for these problems with falling things or throwing things to choose the height equals 0 line in a convenient way, declaring that point to be the point where gravitational potential energy is 0. Anyway, I'm talking about gravitational potential energy because while this thing is falling, I'm going to say that it's got kinetic energy half mv squared, this little particle blob. That's a blob. Of fluid. Kinetic energy half mv squared. It's also now got gravitational potential energy. I suppose in a way it doesn't. There's a lot of negative signs to worry about, but hey, the thing in chat that Ali said about MGH is I think what I want to write here. I think I want to write MGZ. MGZ is how much gravitational potential energy it's got. It would be positive if the water had gone up. In my picture, the water's gone down, so it's negative, and that's actually a good thing. It's consistent with what I expect to happen. It means that V is going to be bigger than V0. The water's getting faster as it's falling. Anyway, I've got this big idea about how energy works, I suppose. I'm going to put a box around that, and we're going to go over there. Okay. So I've got this idea about how energy works. Half mv0 squared, the initial kinetic energy, is going to balance half mv squared for the velocity later on, and mgz for the gravitational potential energy. Oh, what does m stand for? Great idea. I didn't say. I think m is the mass of the blob. It's a good thing to ask. What's m here? Luckily for us, it's going to cancel out from both sides of this equation, so it's going to not matter what the actual mass of that water is. This is one of the good things about falling, that when you're falling, actual mass doesn't matter. Okay. Oh, is z negative? Yeah, I think I've set this up so that z's negative. I've got z equals 0 at the top of where it's coming out of the tap, and then z negative where it's falling. So I think I expect it to be going faster as a result of all this falling that it's doing. It's not rocket science, because rocket science would be if it was going up and if it was a rocket. This is, if anything, the opposite of rocket science, because it's not a rocket and it's going down. Right, okay. As well as energy, I want to make one last comment about this thing to do with the cross-sectional area. When you turn a tap on, it gets going to start off with, but then if you leave the tap running, which you're not supposed to do, save water, but let's imagine, if you leave the tap running, it gets into a sort of steady state. I think I'm going to be interested in that steady state to start off with. That feels easy. It's this kind of shape that it's in while it's running. So I'm going to look at a sort of steady state. If it's in a sort of steady state, it's not getting wider and not getting narrower. I'm watching the bit where it's in this kind of steady pattern of flow. Then I can say something about how the velocity relates to the area. This is what I'm looking for. Yeah, some sort of equilibrium, I suppose. Water's not always like this. Somebody earlier said turbulence versus laminar flow or something. So water can do this thing, fluids can do this thing where they set up this really complicated velocity that depends on time, that things change at different times. But sometimes they can set up this really nice flow that just is nice and sort of straightforward. This flow, I'm assuming everything's just falling straight down. It's coming out of my tap. I'm assuming it's coming out of my tap down. Not sure if that's realistic or not, but hey, it works for now. It's coming out of my tap down. It's just going straight down. It's all flowing downwards. So we can imagine some sort of steady state. No shape change. Or no change of shape. There's one more concept I'd like to introduce to you. Probably you've already heard of velocity and cross-sectional area, radius, all of that stuff, and hopefully also energy. I'd like to tell you about a concept called flux, which is usually given the mysterious symbol Q, and it's equal to, for this problem, A times V. What flux is supposed to measure is how much water is going past a point. I first met this concept in geography GCSE to do with rivers. Rivers, sort of side note about rivers. So rivers look like this. I've been to a river as part of this geography GCSE. You'd think I know what they look like. Not the first time on the live stream that I've struggled to draw a river. That's a deep cut. Right, okay. It's got river banks down the sides like this. And maybe we're interested in how much water is flowing past a given point. is me standing on the side of the river, wondering how much water is going past this point on the river as it's flowing this way, like that. Well, there's kind of three things that are important, I suppose. I've drawn my river very rectangular and boxy, but something probably like, it depends how wide the river is, it depends how deep the river is, and it depends how fast the river is. This kind of idea that what you really need is the, I suppose, area over here. Might be interested in this area over here. I've drawn my river very boxy and rectangular, but maybe I'll be interested in that area in general, and then also how fast the water is going through. That might measure some quantity of how much water is going past per second, or what the amount of water that would pile up if I dammed the river, how much water would pile up per second at this point. For my tap, it's just measuring how much water is, I guess, coming out of the tap. And if we're in a steady state, here's the good bit, if we're in a steady state, then that's constant down the stream. That's the same at different points. This is sort of conservation of stuff. The water's coming out of my tap, and then down here it's leaving the end of this bit of the shape. There's some flux coming in, a flux coming into this bit of shape, and some flux coming out. Steady state means that we've got constant Q. The only thing in this problem that's not a function of Z. So pi is not a function of Z either. We'll keep pi. Everything else seems to depend on Z. Okay, so I've got this flux. I guess I'm saying that for this particular section of the shape, maybe there's 10 litres per second coming in the top, and because the shape's not changing, there must also be 10 litres per second going out the bottom. 10 litres is a lot, that would be very wasteful. Okay, so there's water coming in the top, water coming out the bottom, and if we're in steady state, then it's the same amount of water coming in the top, same amount of water coming at the bottom. Kind of balance of, like balancing forces, but balancing fluxes. Okay, good. So this is going to give me a way to relate together velocities and areas, or the radius, or something like that. So this is going to be an important rule that helps me work out, if I know about the velocity, then I can know about the radius of this thing. I'm going to put a box around this one as well. Right. Yeah, it's like the mass coming in per second. I guess volume coming in per second, if I'm being really precise for mine. Yeah. The units are volume per second, for what I've defined there. People who like dimensions on things, it's cubic meters per second in SI units. Cool, okay. Good. So, time for a little bit of solving. I'm going to rearrange this one. So I've got V naughts, which is something to do with my plumbing, how fast the water's coming out. M doesn't matter. I've got G in here and Z. I'm going to rearrange this one to get V. Okay, I'm going to give myself a little bit more space. If people have missed the start now, here are some equations. Okay, let's see if I can rearrange that in one go. Cancel the M's, rearrange, multiply by 2, subtract 2gz from both sides, and square root, and I think you get this for the velocity. Oh, by the way, I think this is one of the Suvat rules that I've rearranged, by the way. So if you've got something that you've thrown straight downwards, or thrown straight upwards, I suppose, then here's some relationship for velocity in terms of initial velocity. Nothing particularly fluid dynamics-y about this. Blobs of fluid that are falling, maybe they just behave like footballs or something else that's falling. Okay, so I've got my velocity in terms of z. Because of this, it's got some nice square root going on, it's got this z over here. And what I really want to know, though, is not what the velocity is, depending on z. That's interesting, I suppose. It's getting faster as it's going down. As z is getting more and more negative, this minus 2gz is getting bigger and bigger, so this whole thing's getting bigger and bigger. Hello x plus iy. You've missed the setup. We're finding out how big, we're finding out what shape falling water is. What I really want is I want the radius, which is buried into my equations over here. Look, I want this radius. Two-step plan, sort of. I know the radius is related to area, and I know the area is related to the flux. I know the flux is constant. Right, let's try and piece all that together. Flux is constant is the same as the flux coming out of my tap. Really quick question, what is the flux coming out of the top? So flux at the top, I suppose that would be A would be pi r naught squared, and the velocity would be v naught. So that's actually the value of Q in terms of some things from my question about how big my tap is, something to do with my plumbing for v naught. Good. Hi, anonymous person. Okay, that gives me an expression for how big Q is, and I know I can rearrange this a little bit to say, so I've got pi r naught squared v naught, that's the flux, is equal to pi r squared later on. This is the thing I really care about, this area, multiplied by v of z. Okay, and I know v of z from the energy rule. So I've used my energy fact, I've just sort of used my flux fact to say this is constant through the stream of water. We're going to rearrange this for one crazy equation for what shape the falling water is. If you don't follow this next bit, there's just some algebra happening live on a live stream to find the shape of a stream. Right, cool. Here we go. Cancel the pi's and rearrange to divide by this v of z. And I think you get r of z is equal to, there's going to be a big square root as well. So let's do r naught squared v naught divided by, v of z is square root v squared minus 2gz. All of that is then going to be square rooted. Oh my word, I did that too fast. But you know, there we go, rearranging to get all of this. It's pretty mad, right? There's an expression for what the radius is. As z gets more and more negative, this gets bigger, this fraction term on the bottom gets larger, so this gets smaller. It feels kind of all right to start off with. I think we can simplify it a little bit. There's this r naught squared inside the square root, so I can bring that out and maybe even divide. And I'm going to divide top and bottom by v naught as well, and bring that inside here. I think. Again, I'm simplifying really quickly because it's tough. Watching me do algebra live on the stream is not very fun, but also watching me skip algebra is a bit confusing. So I'm trying to do some of it, but not all of it. Okay, I can simplify this a little bit more. This is something like... this is 1 over a square root means thing to the minus 1/2, and then it's square rooted, which is another power of 1/2. And the rule for indices, when you've got one inside another, is to multiply them together. So it's this. Come on, pen. Here we go. Minus 1 over 4. Oh my word. It's actually not too bad once you simplify it down a little bit. So it's that r of z divided by r naught, which is kind of a sensible thing for it to be divided by, is equal to 1 minus 2gz over v naught squared to the minus 1 over 4. That's a prediction for what shape the water is when it comes out of the tap. I can make it look even nicer if you'll let me define a new variable. If we define, and I know that some people don't like it when we just bring in new letters to make things tidier, but if we define some new letter to be, I've got capital L, to be v naught squared over 2g, if I've got all of my parameters in kind of the same place, then this gets really nice, because then I can say that r over r naught is equal to 1 minus z over L to the minus 1/4. L works like a sort of rescaling. If you take the graph 1 minus x to the minus 1/4 and then do some rescaling on it, you can get to this graph. The factor of L is how much you're supposed to rescale by. So now it looks really nice. But partly it looks nice because I brought in a new letter, so I'm not sure how we feel about this. This is a nicer result than I was expecting, I think. It's got some history to it. I think it was first written down by, I can't spell the name. Earlier I couldn't spell Frostrom, so maybe I should not try and spell Weisbach. I think in 55. I think, should have written that in my notes. But what I really wanted to show you was Desmos plot of what this looks like, so we can try and visualize it. So here I've thrown it into Desmos. Let's go full screen. Thrown it into Desmos because why not? What I'm showing you is the function 1 minus z over L to the minus 1 over 4. I've had to explain to Desmos that I would like plus or minus that, and I would like it this way round. So there's some slightly funky X, Y, Z stuff going on. And it looks alright. It looks better if I put on, like my original picture. Ooh, yes. If I, like in my original picture, if I put some ellipses on, then it looks a little bit better, right? Because now it looks 3D. This is fake 3D. This is not real 3D. So this is, I think, what, under some pretty simple predictions, water looks like when it comes out of a tap. Slightly narrowing, like the frostum that Rory suggested, but getting slower and slower because this graph gets less and less steep. Something you can do with Desmos is change what that value of L is, which is really just a rescaling, but you can change what happens when L is really big. That's not changing very much on the screen, but now it's kind of straighter sides over here. What does big L mean? Maybe can we get some sort of interpretation for what that means? I kind of feel like I know what it looks like when I do it. So if I make L big, okay, it's kind of like I'm making the tap louder. It feels like the tap's getting moving the slider that way to make L larger. It feels like I can imagine the tap going whoosh, like in a louder noise. I think that's because L, the sort of mysterious variable that I brought in, is something like, let's have a quick look back again. Yeah, it's V0 squared over 2G. So if L's big, then maybe that means that V0 is really big. You're increasing the speed of the tap, the force of the tap, like that. If I make L really small, then I can get weird shapes like this, where my plot's not so good. It sort of gets narrow quite quickly as the water comes out of the tap. So this is like a very slow running tap. And at some point down here, you start asking questions like, it sort of stops feeling realistic at some point over here. The water's coming out of the tap, but here L is so small, V0 is so small for this picture, that the water, it sees this big tap that I've got turned on, with not very much water coming out, and there's so little flow that it's all in the middle as it starts accelerating away quickly. Yeah, let's have a chat. Oh yeah, okay, so I said it before this came into chat, I think because of stream lag, sorry, but anonymous person is correct. Larger L means faster initial velocity, more violent. Other comments on my model, please. Let's get a few. I can see SV's put one. I can take some criticism. Also, this is from the 1800s, so we've done some more math since then. Yes, Alfie and SV have suggested the same thing, that when you run a tap really slowly in real life, it doesn't do this. It doesn't do this, it drips instead. So L's not quite the speed of the water technically, it's related to the speed of the water. L is, I'll show you one more. L was something I brought in as a convenient letter. It means V0 squared divided by 2G. I wrote it there partly to make it look simple, partly so that I could show this to Desmos and only type one letter of the alphabet, and partly because it is a length. This has got something to do with lengths. It's called a length scale for the problem. This length comes up sometimes when you're doing SUVAP problems for projectiles. It's just a sensible thing that if you see it, it's a length. Okay, but it's big when V0 is big. Yeah, so this tap will start dripping. It's important when you make these models. Even this one I've got questions about, because I'm still assuming that the water would all be really well behaved as it came out of this tap going really fast. When you make a model, it's important to think about what you've included in your model and what you've not included in your model. So in between, I think this looks not too bad. It looks vaguely realistic for what it might look like for a tap going at some sort of medium speed. But perhaps this is less realistic when L is small. So there's a good thing that's come out of this, by the way, is that we've identified that I think it's L that matters for the problem. I've only got one slider really, because the only thing in my shape answer is this L in here. I guess I could change R0 for how big the tap is at the start as well. But it's only really L that's controlling what the shape looks like relative to the initial shape. So we've identified this important parameter that maybe we could have guessed from the start. Yeah, so I haven't allowed for... Okay, thanks Rory as well. Let's put a list of some things that I have not included. Splashing, or let's go sideways motion. Sideways motion is important in a strange way. So sideways is important for this kind of splashing thing that Rory is describing. And also when, anonymous person says, when it hits a flat surface or the back of a spoon or something, then you get sideways motion. You get things going in different directions. Something to look up if you want to see slow motion photography of that is the technical term. It's worth looking up I'm telling you the technical term because researchers working on this put technical language in their papers, but their photos are really good. They've got all the slow motion cameras. So if you search for jet impinging on surface or something, you can see some cool experiments with hitting things. We are ignoring air resistance, as feels like the sort of free space on a bingo board. Air resistance is, I think, surprisingly not that bad to put into this. You can imagine the air coming, maybe being brought down with the water as well. You can put some extra terms in to allow for that. Yeah, constant flux breaks down if there's very low flow. I think I'd like to get a physics thing going on in there. I'm going to put in friction because, again, it's something people keep saying. Friction with the sides of the tap is an interesting thing because I've got that down as, I guess, a sort of separate concern about how does the water come out of the tap. I've assumed that it's just V of Z. It only depends on Z, but if it's going slower at the outside and fast in the middle, then, well, that's a bit different. There'll be some velocity that depended on X and Y as well. Oh my word, between them, these two features of sideways motion and V depending on, velocity depending on X, Y and Z, between them they make fluid dynamics really interesting. That there's this idea that velocity can depend on where you are in 3D space, and also the velocity itself can have three components as a vector. It's sort of really high complexity thing. Friction is an interesting thing because it's important where it meets the tap. It's also friction, I'm going to say, internal as well. Anonymous person in chat has just said cohesion of water. Water's sort of sticky, I think, is what they mean by cohesion. It likes to stick together. Maybe that's a tension. No, okay, let's go with internal friction. There's a couple of effects to talk about. Water's got some internal cohesion and also some internal friction. There's something called viscosity or sort of stickiness, which is maybe not so important for water, but if we repeat this experiment with honey or something, or some really sticky fluid like tar or lava, then it's much more exciting, and the fluid's got a lot more internal friction that affects how the velocity profile works, whether it depends on X and Y, and also affects, that's not true, it doesn't affect so much whether it depends on X and Y, it affects basically the pressure profile and the distribution of forces within the fluid. Do we take Z as constant? I think Z varied down the streams. That was all right. Thank you, Imi, in chat as well. Cool. Yeah, so I think there's a physical thing called surface tension. Surface tension is quite strange. It's one of the main things in research that I did back when I was doing research. Surface tension has got this quite strange aim that surface tension would like it if all of the water was near all the other bits of water, which tends to make water form spherical droplets if you leave it alone. What surface tension would actually like is surface tension would like it if all of the water in the universe was all in one sphere. That would be ideal for surface tension, and sometimes it feels like that's what surface tension is trying to achieve. It doesn't like these long cylinders so much. Long cylinders, not so good. Splitting that up into droplets that we can maybe later join together, who knows. Maybe that's something that surface tension wants. But surface tension, seriously, is, you can think of it as a force. Water molecules are attractive to each other. So near the surface, where there's water molecules on one side and not on the other, that tends to create some sort of effect of a net force that manifests itself in this sort of tension surface effect. Good. Okay. So surface tension tends to make, especially slow running streams, into droplets. Great. Good brainstorming of things. I'm always in two minds about these sections. We've done them before as well. When I talk about a physical problem with some maths, and then we talk about reasons why it's bad or reasons why it's not good enough. I'm in two minds because on the one hand, this is an important skill, being able to analyse the model that we just had, work out its weak points and say what we could change for another time. On the other hand, I'm not going to do any of this now, so it's a bit of a downer. It just sort of feels like, there's some other stuff that we're not doing. I think I want to highlight that this result for the shape is pretty cool and it's pretty good. I think it actually works quite well. Right, okay. What we should maybe do is go back and compare this to some photos of water coming out of taps or something like that to see, does this simple rule do a good job of explaining what water looks like when it comes out of taps. Same effect as a stretched diaphragm. That is a tricky question because I don't know what you're imagining doing with the stretched diaphragm. Same effect on something. Okay, right. I think we're going to call the water there. I've given you one thing to look up if you want to see stuff happening. Back when this live stream was starting and new, we used to talk about ad breaks. We're going to take a very quick ad break. The ad break is going to be what if two streams collide? And it's an invitation to go and find out what happens, maybe by looking up what happens for jet streams colliding. Depending on angles and depending on velocities, you can get lots of different things. There are some great research papers out there, which, the research is quite advanced and complicated, but the pictures that they're trying to understand are really cool. I think I am going to mention a blog. I'm in two minds about a lot of things today, but I think I am going to go and mention a blog. It's called FY Fluid Dynamics, and they've reported on research several times on different aspects of this problem. So the blog's called FY Fluid Dynamics, and it's just images of cool bits of fluid dynamics. I think it started out on Tumblr, but I might be wrong. Yeah, it's one of my favourite websites, especially when I was doing my PhD in fluid dynamics. Okay, assessing limitations is a pivotal reason why science has progressed. Yeah, I think our ability to look at things and say, no, do it better, is good. And some of the things above we can actually do, we can work on. It's surprising what's currently where the cutting edge is. I think the cutting edge is still including friction and surface tension into this model. I think might be active research. I found a paper from not too long ago suggesting that it's complicated how you put both of these things into a model at once to work out the shape of a falling jet. So if you're working on a problem where surface tension and viscosity are both important, then that could be a complicated problem. Is there a fluid which takes years for a single drop? Yes, there's this pitch drop experiment, which is a very, very sticky fluid that's very, very slowly dripping over the course of about 50 years. They've set up this experiment where it's supposed to drop very slowly. Earlier when I said that using tar instead would be exciting, that was a poor choice of words. Using tar instead would be very, very boring. Right, okay. How are we doing for time? We're doing okay. I think I've got enough time to do something completely different, just in case. Yeah, so there's something else to search up. What happens when you add two streams together? And what happens if you have a very, very viscous fluid? Okay, let's get rid of this and do one other thing, and then that'll be the end of season 3. Yes, delete all content. Right, okay. So, a few weeks ago on the live stream, we talked about a different problem. It was something to do with squares and laying out a 4x4 grid under certain properties. I'd like to revisit that problem to talk about one aspect of that problem. I'm not going to give away the answer to the problem from a couple of weeks ago, but I'm going to give you some help trying to analyse that problem. Okay, so, sort of reminder of what we'd like to do. I've got letters A, B, C and D, and I'd like to put them in a 4x4 grid. 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4. Using sort of Sudoku rules, where I'd like to put the letters into the grid so that each row and each column contains one of each. Okay. Yeah, teacups. It's like the teacups problem from a few weeks ago. If you were here for bridges and teacups, which was a fun episode looking at some problems, there was a teacups problem we didn't finish. I decided not to spoil the answer. I'd like to think about these. We started thinking about some case-by-case stuff about how you might achieve this. So you might start writing some letters in and trying to make sure that you've got one of each in each row and column. So I've got one of each in this column here. So I could do something like this. But now it's getting a little bit scary because I've got A and D here, so maybe I want a B and a C here. We can sort of fill things in as we go. I thought it'd be fun to do a sort of systematic look through at the solutions to this. I looked it up on Wikipedia just before going live, and in some sense there are exactly 4, which is a small number, so we should try and find them. That's my plan for the next 10 minutes. I'm going to try and explain the sense in which there are 4 of these, 4 solutions. There's some more stuff I need to say, and then we're going to try and find the 4 solutions. Okay. That makes sense? Yeah, these are called Latin squares, I think. I can't remember what a Greco-Latin square is. I recognise that term, but I can't remember why it's different from a Latin square. I think this is just a Latin square. I was on the Wikipedia page for Latin squares. Right, okay. Here's the sense in which there are 4 of them. So let's say you've got a solution. The top row says A, B, C, D in some order. It's got to. It's got one of each A, B, C and D. Now you get a solution. What you could do for your solution is you could swap 2 of the columns. That would still work because the columns would still be fine and the rows still contain the same things. You can swap the columns, and what you could do for any solution that you found is that you could swap the columns around so that the top bit reads A, B, C, D. You could do that. So whatever solution you've got, you could rearrange the columns so that they read A, B, C, D along the top. The opposite statement of this is that if I find solutions that say A, B, C, D along the top, then I can rearrange the columns to get to your solution by reading across the top row of your solution and saying, right, all I need to do is rearrange the columns and I'll get some other solutions. Okay, yeah, so there's some other stuff going on to do with, yeah, other stuff like that. Okay. Next, I'm going to play a game with the rows that this first column says A, B, C, D in some order. So what I can do is I can rearrange the rows so that they say A, B, C, D down this side as well. So bear with me. Whatever solution you've got, you can rearrange the rows and rearrange the columns. Rearrange the columns and rearrange the rows so that you get A, B, C, D along the top and A, B, C, D down the left. You could do that. There's a slight bit of calculation to say, if I find the solutions that look like this, then I think I can turn them into all of the solutions by rearranging the rows and rearranging the columns. Oh, there's a solution. Okay, so here's a solution in chat. Let's quickly check it. CADB. Oh, well done, chat. It's only been... Somebody told me once that they were anonymous in chat. I've written that wrong because I can't write while talking. Anonymous in chat if they were not sure, but they were used their own name if they were proud of something. This looks to me like the sort of thing you should be proud of because it's got an A, B, C, D in each row and in each column. Hooray! Okay, I can shuffle that around just to demonstrate what I'm thinking of. I can take this solution that chat's given us, which does work, right? Yeah, brilliant. Oh, well done, chat. I'm now going for a sort of collective responsibility. Yeah, thumbs ups on that one. Thank you. I can rearrange your columns a bit, like this. A, C, D, B, and then I'll take the one that starts B, and then I'll take the one that starts C, and then I'll take the one that starts D. And I can rearrange your rows to get A, B, C, D along the top, and then I'll take the one that starts B, and then I'll take the one that starts C, and then I'll take the one that starts D. Okay, this is what I want to try and find. I want to find solutions that look like this. A, B, C, D along the top, A, B, C, D down the left, and then if we feel like it, we can start shuffling the rows and columns to get other solutions like this one in chat. But I'm going to get it in this format, with these things kind of pre-filled in. Okay. That's the sense in which there are exactly 4. We're going to try and find them now. I think I'm going to copy this because I might need it in a moment. If I was clever, I would copy it exactly 3 times, right? Stick one over here for safekeeping. Group that together. So this is a perfect time to get good at Miro, isn't it? Okay, we've got a couple of copies of that, so I'm not scared. Okay. Let me group these ones as well. 7 minutes left on the clock. 4 of these to go. Working systematically is really important. Working systematically is really important. We could start thinking about the possibilities for this square. So now we're really sort of playing a Sudoku game, right? Except it's not a unique solution, so not quite like a Sudoku. This could be A or C or D. There's quite a lot of possibilities. Let's look at the next square. This could be A or D. This could be A or C. And they can't both be A. So I can already see some possibilities. I'm going to keep track of them in different colours and in different corners. Oh, this is ambitious. Why have I said that? This is too much. Okay, so I can have A up here or D. I'm not going to do that. I'm not going to stick to this. I've got 2 possibilities. I'm not doing different colours. A or D. If this one's A, then am I stuck? I might be stuck because if I put an A here, then I would have to have... Oh no, I'm not stuck. I could put a C here, can't I? I could put D here. I have to avoid being stuck. I can work around it. B, D, and this could be an A. This could still be an A or a C in that case. And B, D. Okay. So if this square here is an A, could have been a D, but if it's an A, then I can start filling stuff in, which feels good because now I've got BD, A, C, and I can do CA and DB. This has really become a Sudoku test. Okay, I've got something as a solution. Oh, A, B, C, D, B. Oh, Alfie, this is not the solution that I've got. This different solution. B, C, D, A, C, D, A, B, D, A, B, C. Yeah, that looks good to me. I'm going to try and find that one in a second. So I'm working systematically on this purple box. I found it's either an A or a D. If it's an A, then I can fill in the rest of the grid. If it's a D, I'm going to need something else. So separate case where I put D inside this box. Okay. Okay, so I found one solution. Analyze it in a moment, think about what it looks like. But I want to think about what happens if that's D. And I think I've got two options, because I think this could be over here, either an A or a C. If it's an A, am I done? Or not quite, because I've got BA and then DC, and then I've got CD, and I've got band CD, and then I'm not sure what to do in the bottom corner. If I take this C over here, BCD, I would put maybe an A over here. This is less fun than I thought it would be, sorry everyone. Something like this, BCDA, and then I've got some C's and D's, and in the bottom right case, where I put a C over there. This one's the other way around, and then either way this turns out to be a D. Down the bottom this is the other way around, and then over here I suppose, what have I got? In the bottom right corner, if I was in the case where it's D and then A, then this would be B because it's not C. This would be A, this would be B, this would be A. B, C, D, A. This is Alfie's solution. C, D, A, B, D, A. Oh no, I've messed up. Third row, yeah, okay. I've messed up. I've got too many A's. Help, chat. I don't know why I thought this would be a good idea. Is this a C? This was a C all along. This was a C. Okay, due to chat lag, chat is now going to help me, but we'll get there. Okay. I think I just messed up the last thing I wrote. Yeah, I think I did. This bottom right case got a bit confusing. Okay. This is how I do Sudokus as well, with the little numbers in the squares. Okay, so final remaining case. I've got in the top case up here, I've got A up here, D, C. I've decided on this bit, and then the bottom right corner I haven't solved yet. So this is my last case. I've got two A's to go and two B's to go. Yes, thank you, Anthony. Due to chat lag, I waited out, but we got there. Thank you. Thank you anyway. This bottom right corner, I think it's got two A's and two B's in it. This is a really pretty one actually, isn't it? But I think they could be either way around. So I think this is AB, BA, or BA, AB. So I think those are two possibilities. Oh my word, I think I've bashed through it. I've got my original picture with a solution in, and then I've got this kind of solution in the bottom right corners, and then I've got two solutions to do with having the A's and B's. I love these ones. Having the A's and B's in their own little squares, like this. Can you see this sort of structure? The A, B's up here, it says ABBA up here, and then it might say ABBA down here, or it might say BAB over here. And I think that gives me 1, 2, 3, 4 different solutions. Hooray! If you would like long and complicated homework there's a couple of weeks break before the start of the next season of Maths Club. Wikipedia tells me that for 5x5 versions of this problem, A, B, C, D, E, ones that go A, B, C, D, E along the top and A, B, C, D down the E down the left, for 5x5 versions of this problem, there are 56. So if you would like to try and find all 56 of those, the one person in chat who thinks this is fun, there's some homework. If you want an easier problem to try, for 3x3, just ABC, Wikipedia tells me there's only one. So again, checking out all the possibilities. Relating back to the teacups, I've now got some ideas about what that Latin square, or what the grid, Sudoku grid for what the sources could look like. The teacups problem says that we've got some teacups on sources, we'd like the sources to obey these rules, we'd like the teacups, 4 different colours of those, to obey these rules, and we'd like to see every combination of saucer and cup. So what we're looking for is a grid a bit like this for how to lay out the saucers, a grid like one of these for how to lay out the teacups, and we'd like to make sure that they kind of never agree in any places. I suppose we don't need one like this. We're allowed to shuffle the rows and columns around for our teacups, and in fact we probably do want to do that, because if I just stick two of these together, I'm going to get B on top of B in two different places. So I probably do want to shuffle some stuff around. Sneaky combinatorics question mark, since it's a question mark in chat thing. Sneaky combinatorics question mark is, here's the combinatorics question that I'm sort of avoiding. There's a relationship between how many of these there are with the columns laid out ABCD, ABCD. We found there are 4. Versus how many solutions are there to the original problem where the top row could say anything and the first column could say anything. There's a relationship between those. I want to say it's not obvious, because the first time I tried to work it out I got it wrong. Maybe that's not a great way to decide whether things are obvious or not. It wasn't obvious to me. There we go, there's an honest way of saying it. The kind of combinatorics of this problem that I've solved on the stream, where there's 4 as the answer. What's the actual answer for how many Latin squares there are where you're allowed to put this first row in any order and the first column in any order? Not the first guess that I had anyway. Okay, cool. I think since it's 6 o'clock, I've left you with some different directions to take this, trying 3x3, trying the original Teacups problem again, trying 5x5 if you'd like to smash through 56 cases, or trying to explain the relationship between these two versions of the problem, sorted columns, not sorted columns. Lots of different directions to take that. And at some point during the break, further reading for recent episodes is going to appear on the Maths Club website as well. Links are all currently broken, but we're going to sort it out. If you've joined us for the first time today, there are about 30 other episodes just like this one, looking at maths problems, usually with other people joining in as well, to present some mathematics on a huge variety of topics. And on the Maths Club website, link in the description and link on screen, there's further reading for most of them. And for recent episodes, further reading coming soon at some point. We're going to take a couple of weeks break, and we're going to be back on the 21st of April for what I'm calling Season 4 of the Oxford Online Maths Club. It's been a pleasure talking to you about maths for the last term, and after the break, we'll see you again. So we're going to call that Season 3. Happy Easter and happy holidays, if you get some holidays as well. We'll see you back for Season 4 starting in 3 weeks' time. I love calling them different seasons, even though, here we go. It's somebody's birthday. There we go. What more could you hope for than Season 4 of the Oxford Online Maths Club? Thank you, Emily, for moderating chat, and we will see you possibly at an open day. Open day, not sign-ups are still open. Gotta remember all the things. This is a mess. It's always a mess at the end of these. Take care, have a nice evening, have a nice 3 weeks, and we will see you for more Maths Club in a bit. Bye.